Good afternoon, everyone. Can you hear me? Sound check. Hello.
Yes, sir. Sir.
Good afternoon, sir.
All right. So I may request, okay, to those who are able to open your respective videos. Okay. And by the way, my PC is lagging and my other device is camera is not working properly. So I'll be off cam right now. So to those who are able, please open it and then so that masyada akong discussion. So okay, today we'll be having entirely new topic. Okay, and we're already in Unit 2 of General Physics 1. Okay, so Unit 1 is all about the physics, the units, physical quantities, measurements, and the errors. Okay, so today we'll be having this topic, okay, about mechanics. And it is, okay, mechanics. So it is one of the branch of physics that deals with motion and energy and force. Okay, so today we'll be tackling the first topic in mechanics, and that is all about kinematics, motion in one dimension. Okay, so here we have, all right, so next page. Okay, so let's have the objectives for today. So first, let's handle before we proceed to these objectives, so first, let's define kinematics. Okay, so you can try to search it, okay, sa definitions of kinematics. So let me have some prelude or just say some initial thoughts regarding kinematics. So of course, objects are in motion everywhere we look. Everything, okay, so for example, from a tennis game, the space probe flyby of the planet Neptune involves motion. When you are just resting there, your heart moves, okay, moves blood through your veins. And even in inanimate objects, okay, there is continuous motion in the vibration of atoms and molecules. Okay, questions about motion are interesting in and of themselves. So for example, I have a question here. How long will it take for a space probe to get to Mars? Okay, so that is an example of the questions regarding motion. And another, you also might be wondering, okay, when you are watching a football game, where will a football land if it's thrown at a certain angle? Okay, so to answer this question, we need an understanding of motion. And that is the key, okay, in understanding the other concepts in physics. An understanding of acceleration, of course, crucial if you want to study forces. Okay, so of course, we need to have formal study of physics begins with kinematics. So have you searched for kinematics? Okay, anyone, what is the definition of kinematics? What do you think? Anyone? What do you think is kinematics? Okay, anyone? Have you searched it? Oh yes, isa ko kabantay. All right, so let's have Sophia.
Kinematics is the branch of classical mechanics that describes the motion of points, objects, and systems of groups of objects.
All right, so it is a branch of classical mechanics, of course. So we have a quantum mechanics, and there's also a classical mechanics. So kinematics is a branch of classical mechanics that deals with the study of motion. Okay. However, when you're going to study motion, you're not going to consider what causes that motion. That is kinematics. Okay. If you want to know what is the cause of those motions, okay, that is already another branch of classical mechanics, and that is dynamics. However, right now we'll be focusing in kinematics first. Okay. So again, kinematics is defined as the study of motion, without considering its causes. Okay, so from the word itself, kinematics, it came from the Greek term meaning motion. And of course, it is related to the word cinema. Okay, kanang cinema. Okay, and kinesiology, okay, the study of human motion. Okay, so kinematics, okay, related terms are cinema and kinesiology. Okay, so as you know, cinema, okay, is a motion pictures. Okay, so the same, it deals with motion. Okay, you don't need to consider the causes of those motion. Okay, you just want to study the motion itself. All right, so that is kinematics. And right now we'll be dealing with, okay, the basic, okay, kinematics, and that is the one-dimensional motion. Okay, one-dimensional motion. Okay, so we'll be studying it in just one dimension. It could be in the x dimension or the horizontal dimension, or it could be in the y dimension or in the vertical dimension. Okay, it could be either of the two, okay, dimension. All right, so these are the things, okay, you need to know about kinematics. Okay, and of course, there's also another term for motion in one dimension. As you can see, motion in one dimension, okay, it could be also called as motion along a straight line. Okay, as you know, one dimension, just one simple straight line. All right, so motion along a straight line or one-dimensional motion. Okay, so let's now proceed to the objectives for today. First, okay, we need to learn about displacement and velocity. Okay, so what are we going to deal with right now is to describe motion in terms of displacement, time, and velocity. And then we're going to calculate the displacement of an object traveling at a known velocity for a specific time interval. And then we're going to construct and interpret graphs of position versus time. Okay, so I think we're just doing the interpretation of graphs. And for the construction, it is a bit harder unless, okay, I'll be looking for tools, okay, online tools, okay, later on, okay, so that it is much better if you can construct your own, okay, position versus time graphs. All right, so let's now proceed, okay, in discussing the different concepts. So first, okay, we'll be dealing with these concepts all throughout our session today. So we need to know frames of reference, then the vector versus scalar quantities. And I know already understand these things. Next is displacement, velocity, both average and instantaneous velocity, acceleration, also both average and instantaneous acceleration, and finally, we're going to have the graphical representation of motion. Okay, so right now, we'll be dealing with reference frames. Okay, always remember this, motion is relative. When we say an object is moving, we mean it is moving relative to something else. So for example, you are walking, okay, on the street, okay, so you are moving relative to the street, okay, or just say you're moving relative to the earth. Okay, so we just generalize the street, the ground, etc. as the earth. Okay, so you are moving relative to the earth. Okay, so that is reference frames. Earth is one of those reference frames. However, what if you are inside in a moving vehicle? Okay, when you are walking inside a moving vehicle, let's just say the example here, you're moving inside a train. So in this case, the reference frame right now is not the earth, but instead the train, because you are inside, okay, the moving train. Okay, and this train, when you are just sitting down, you're not in motion at all. Okay, relative to the train. All right, you're not moving at all relative to the train if you are just sitting down there. However, when you start moving, okay, from one location to another, then you are in motion relative to this train. Okay, So of course, when someone is looking at you outside, you are in motion. Even though if you are in motion, even though you are sitting there in the train, because in the perspective of someone outside the train, you are moving. Okay, so that is what we call motion is relative. Okay, I think it is a bit harder to understand. So I want some just say questions. Okay, do you have questions in understanding what I want to understand regarding the reference frames? Anyone? Questions?
Kuan sir galibo katong sa train nga parts.
Right. So ako'y balik. So first, okay, let's just say you're inside. You're just sitting down there inside a train, inside a moving train. Okay, let's be specific. Inside a moving train. Okay, in the perspective of the train, you are sitting down. You are not in motion. So meaning, if the reference frame is just the moving train, you are not in motion. Okay. However, when someone is looking at you outside the train, okay, outside of that moving train, then you are in motion. Okay, because you're together with the train. Okay, so that is a matter of reference frames. Okay, and then if you start moving, so inside the train, of course, okay, you are in motion inside the train, and then someone is looking at you outside, then you are moving faster compared to the train. Okay, so because you're going to add the moving train plus your the direction of your motion and the speed and direction of your motion. So meaning you are actually faster if you're going to move inside the train. If you're going to if the perspective is someone is looking at you outside the train. Okay, so always remember motion is relative. Okay, so most of the time we'll be dealing with motion relative to the earth. Okay, anything that is not moving. Okay, so for example, the ground, okay, the park, okay, the road, etc. Those are part of the earth. Okay, as long as that object is not moving. Okay, so you're in the reference frame of the earth. Okay, when you are inside a moving vehicle, then your reference frame now is that particular vehicle. All right, so that is all about reference frames. So any other questions regarding this reference frames? Anyone? Okay, so I think wala na yung isa. So let's continue with the next concept. So I already know about this scalar and vector quantities. So let's have a short recap regarding scalar. Okay, scalar quantities only have the magnitude. For example, the speed contains as a magnitude of 15 meters per second. And for the vector quantities, it got both magnitude and direction. So meaning it has velocity and velocity, for example, so it got 15 meters per second north. Okay. So these are scalar and vector quantities. Next up is displacement. Okay, so displacement, okay, is the position of an object is specified during, using a coordinate system. Okay, if you're going to plot, the position of an object inside a coordinate system, okay, we will know that displacement is a vector quantity. Okay, and it is all about the change in position. Okay, so meaning it is a change of the location of that object. Okay, if you're going to plot it inside a coordinate system. So for example, someone is located at point X and then it starts moving to point Y. So meaning, there's a change. There's a displacement in that case. Okay, however, we'll be using only X. Since this is one dimension, so we'll be using only a single variable. So let's represent the horizontal line as X variable. Okay, so all horizontal motion. Okay, so let's make all of the motion. Okay, if ever there's a problem solving, so let's place them inside a one horizontal line. All right. So let's place everything inside a one horizontal line. Okay, since we're dealing with displacement in one dimension. Okay, so always remember the direction and the magnitude of the displacement is always specified in the coordinate system. Okay, so what are the directions in this case? Anyone who can tell me? What do you think are the directions, okay, of this displacement in the one horizontal line? Okay, what are the directions? Okay, what are the possible directions you can have in one horizontal line? Okay, now coordinate system. Anyone? Okay, yes, isa po ni isa. Okay, yes, there is.
Raira, sir.
Yes, is that right?
East, north, west, and south.
No. Okay, so it just only the east and the west, or okay, in a term, let's just say left or right. Okay, so to the left and to the right. Okay, it could be either of the two, because in horizontal line it could be either. Okay, when the motion should be either in going towards the left direction or towards the right direction, east direction or to the west direction. Okay, so east or west or left or right. Okay, so these are the two directions when we are making the motion, okay, placed inside a one straight horizontal line. Okay, and of course it is independent of the path taken by an object. Okay, so it doesn't matter, okay, what paths the object has taken, since okay, we're dealing with one dimension, so we can also have different positioning of the object. So for example, at some point +1, and then he had to shove -3, and then he proceeds to +5, and then he goes back to -5, something like that. So the path, okay, those are the paths. Those are examples of path, okay, inside a one straight horizontal line. Okay, remember a number line. Okay, a number line, horizontal number line, it composed of a 0 and then positive x, so positive number to the right and negative numbers to the left. Okay, so the movement could be either left to the left or to the right. Okay, so we can have, okay, we can choose some, for example, +2 meters and then -2 meters. So +2 meters means that, okay, it is moving to the left, to the right. Okay, positive number, okay, determines that the direction is to the right, and negative number determines that the direction is negative. So, okay, in other words, the signs determine the direction. Okay, again, the signs of the sign, positive or negative sign, okay, determines the direction of the motion. Okay, this is especially useful in one dimension. Okay, so examples of paths taken by an object, so +2, and then he goes to -3, then he goes to +6, and then he goes to -5. Okay, those are paths. Okay, however, displacement is independent of the path traveled by an object. Okay, because, okay, displacement is just the shortcut, the shortest distance from the initial position towards the final position. Okay, again, displacement is the shortest distance, okay, from the initial position towards the final position. Okay, so here right now, okay, we will be having a variable, okay, delta x, okay, means this is the displacement change in position. So from the word delta, it means change in something, and then x is the position, okay, of an object in the horizontal line, and it is equal to, okay, x sub f. Okay, this means that this is the final position minus the initial position, xi. Okay, or some books can also have something like this. Okay, so delta x is equal to x minus x0, where x here is just the final position and x sub 0 is, okay, the initial position. Okay, so, well, as long as you know what you're, okay, placing it at, okay, usually xf, x2, x1, okay, you can also use them. Okay, x2 minus x1, okay, you can also use them. Okay, because x2, you know that this is the second, or this is say final position, and x1 is the initial position. You can also have that. Okay, so displacement, okay, as long as you know where is your initial and final position, the variable doesn't matter really. Okay, so the formula is always final minus initial. All right, again, final minus initial to get the change in position or displacement. Okay, so let's have an example in this case. So in this case, let's have this one. Okay, so we have here a teacher. Okay, and there's a green board. Okay, green board, yeah. Okay, so the teacher is the position of a teacher in this coordinate system is initial position is equal to 1.5 meters, and the final position is 3.5 meters. As you can see in the in the in the number line below, okay, in the Cartesian plane, this is a Cartesian plane. So let's focus on the number line, the x-axis rather. So this x-axis here, you will see the label, okay, of x0 and xf. Okay, to determine the displacement of the teacher that moves from 1.5 meters towards 3.5 meters, you just simply, okay, subtract, okay, 3.5 minus 1.5, and the answer is positive 2.0 meters. Okay, so this positive sign here means that the object is moving to the right. Okay, and then this 2 meters is what we have, what we call the magnitude. Okay, so in a sense, displacement is a vector quantity. Okay, so questions, okay, regarding this example? Okay, so I think wala questions. Wala ba? Yes, wala questions. So, okay, so next up is we're going to differentiate distance and displacement. Okay, so first let's define distance. Distance is the length of the path that an object travels. So in general, distance is actually, okay, the total length of the path that an object travels. Okay, this is path dependent. Okay, so you need to follow all the path. Okay, and the direction doesn't matter. So in this case, ang positive, the positive and the negative sign doesn't matter. You need to have the absolute value and add everything. That is the distance. All right. Again, path dependent. So meaning direction doesn't matter. You need to add everything. Take the absolute value. Okay. Okay. In this case, in the one dimension. And for the displacement, of course, just simply calculate the shortest distance, okay, from the initial position towards the final position. So for example, here I have a straight line, and then I'll be plotting this inside a Cartesian plane, and then here, University Station towards the Typo Market Station. So the train is actually passing through these winding roads, okay, of a total distance of 6.7 kilometers. However, the displacement right now is actually 5.4 kilometers. Okay, so that is the displacement. Okay, so positive 5.4 meaning it is going, well, to the right direction, or could be going towards the north. Okay, when remember, motion is relative, so we can actually place our coordinate system. Okay, we can rotate it. Okay, and then place the x-axis differently. Okay, as long as inside the map we can plot out the x-axis. Okay, so that is the difference between displacement and distance. Okay, distance is just a scalar quantity. Displacement is a vector quantity. Okay, so before we proceed to time, so any questions regarding distance and displacement? Okay, so I think there's no more questions. So yes, okay, we're going to first describe motion. Okay, of course, describing motion requires a frame of reference. So most of the time, okay, the frame of reference, okay, will be the earth. Okay, the ground, the park, the road. Okay, that is relative to the earth. And then when you are inside a moving vehicle, then your frame of reference now is that particular vehicle. Okay, so this is still a continuation with displacement. So we had here an example. Okay, position is determined with respect to the origin. Okay, displacement with respect to x1. All right, so we had here x1 and x2. So let's just estimate the values. So for example, here we had the first one, okay, the top left, okay, the top left. So let's have x1 going x2. x1 is around 1.5 meters, and then x2 is, okay, we can estimate it into 4. So 4 minus 1.5, and we had the displacement equal to 2.5 meters. And then, okay, it is already understood that it is positive. So delta x here, or the displacement, is going towards the right direction. Okay, so let's have the top right, okay, diagram. Okay, so the top right figure, okay, it started from 5 meters and ends up going towards the 1 meters. Okay, so 1 meter is the final destination. So 1 minus the starting 5 is equal to -4 meters. Okay, meaning this negative sign here that means that the direction is going to the left. Okay, with a magnitude of 4 meters. And let's proceed to the bottom left, okay, of the diagram. So here it started from -4 going to the -1. Okay, so here in this case, -1 is the final destination, and then the final destination is the initial destination is -4. So -1 minus -4 is equal to 3 meters. Okay, so it is actually going to the right. Okay, so remember, okay, it doesn't matter if the position starts at the negative side. Okay, as long as it is going to the right, the motion is as long as the motion is going to the right, then it is positive. And when the motion is going to the left, then the motion is negative. All right, so it doesn't matter where the position of the object is at first. Okay, it matters only when the direction of motion. Okay, so it could be either to the left or to the right. Okay, so that determines the sign. And for the last diagram, we had here -2.5 towards -4. -4 minus -2.5, we had a displacement equal to -1.5. So as you can see here, there are only 2 times that the motion, okay, are going to the left, going to the right rather. Okay, it doesn't matter if it is located in the positive x-axis or the negative x-axis. The same with the second one, okay, to the left. So both of them, okay, it doesn't matter if it's located in the the positive x-axis or in the negative x-axis. All right, so the displacement is always related to the initial position. Okay, so just remember the initial position and the final position, subtract two of them, and you will get the displacement. Okay, so that is how you're going to solve for the displacement. Okay, so there are times that we are dealing with vertical line direction, vertical line motion. So going from this, going towards the north or toward the south direction. Okay, so we can have, but that is also part of the one-dimension motion. Okay, that is also part of one-dimensional motion. Okay, so we can also determine, by convention, the positive and negative. Okay, right positive upwards, negative positive also for the negative left or left and down. Okay, so these are the direction that is being indicated by the sign. All right, so we can now proceed to this one. Okay, so reference frames and displacement. Direction is relative to the initial position. Okay, so that's the reason why just remember the initial position. Okay, because that is your reference point. Okay, towards your final position. Okay, so that determines our displacement. All right, so as you can see in the diagram examples here, so x1 always be the starting point. Okay, so just subtract the displacement of this left diagram here, 30 minus 10, the answer is 20 meters. Okay, positive 20 meters. And for the second one, okay, it is towards the 10. Okay, so this is negative 20 meters. Okay, so 10 minus 30, x2 minus x1. Okay, so these are the relationship between reference frames and displacement. All right, so before we proceed to average velocity, I think I forgot to add the time. Okay, so let me discuss time a bit. Okay, just remember, every measurement of time involves measuring a change in some physical quantity. It may be a number on your digital clock, could be your heartbeat, or the position of the sun in the sky. Okay, in physics, the definition of time is simple. Time is change. Okay, just remember, time is change, or the interval over which change occurs. Okay, so time is the interval by which change occurs. If there is change, there is time. All right, so just remember that those things. If there is a change, there is a time. Okay, so it is impossible to know that time has passed unless something changes. Okay, even though the object is not moving, just sitting there at one point, not moving for a particular time. However, in a micro system, inside that particular object, the molecules are always moving. Okay, so that is already related to quantum mechanics. So we'll not be dealing with that. So just always remember time, is the interval by which change occurs. Okay, so of course, you know the international system, this system international unit, SI unit for the time, and that is seconds. Okay, and then how time is related to motion. Okay, how does time related to motion? Okay, so we are usually interested in elapsed time for a particular motion, such as how long it takes an airplane passenger to get from his seat to the back plane. Okay, so to find elapsed time, we note the time at the beginning and the end of the motion. Okay, so if you want to know the time elapsed, just say the time interval between two events. So the events stated in my example, the time it takes for the passenger to get from his seat towards the back seat of the plane, then the time, okay, so we just take note, for example, he started moving at around 3:36 p.m. Okay, and then he reaches the back seat around 3:37 p.m. So meaning the time interval at that point is 1 minute. Okay, if you want to be more precise, you can do the seconds. Okay, in that case. So that is how we solve for the time interval. Okay, that is the time it takes. Okay, time interval or time in general, that is the time it takes for the passenger to get from his seat to the back seat. Okay. So for example here, okay, I'm doing a Zoom meeting, started at 3 p.m., then end up at around 4:30 p.m. So the elapsed time might be equal to 1 hour and 30 minutes. So that is our elapsed time. Okay. So the elapsed time can be determined, okay, between the time at the end, okay, the time at the end of motion, and then the time at the beginning of motion. And usually, we always place the initial time equal to 0. Okay? We always place the initial time equal to 0. That's the reason why the time interval is just simply equal to t. Okay? T, okay, that is the symbol for time, just simply t. Or just say the time it takes for one object to reach a particular motion or the end of motion. Okay, something like that. Okay, so that is all about the time. So now we're dealing with average velocity. So already discussed time interval, time elapsed, okay, and displacement and the distance. Okay, so there are two concepts you need to differentiate. The first one is average speed and average velocity. So for speed, how far an object travels in a given time interval. Okay, so how far, okay, an object travels in a given time interval. So that is the speed. So this should be how fast an object travels. Okay, how fast an object travels. Okay, so that is the general definition. Okay, so in operational definition, or the operational meaning how you're going to measure it, that is the operational definition. So the operational definition of speed is simply the distance traveled over the time elapsed. Okay, so that is practically what we call the average speed. Okay, average speed of an object is just equal to the distance traveled by an object over the time elapsed. And then it just only means that speed is a scalar quantity. Okay, direction is okay, direction doesn't matter in this case. However, for velocity, we need to include the directional information. So hence, we need displacement divided by the time elapsed. And for this time elapsed, we can simply use equal. Delta t is just equal to t, as long as it is not specified in the problem that there's a time interval. Okay, so if there's a time interval, for example, t1 is equal to 2 seconds and t2 is equal to t sub 2 is equal to 5 seconds. So that is a time interval. So you need to subtract them to get the time elapsed. Okay, again, to get the time elapsed, it is simply delta t, okay, is equal to final minus initial. Okay, if there's a time interval given in a problem, that's the point by which you need to subtract the two. However, if just simply time given, for example, okay, a car travels 150 kilometers in 2 hours. Okay, the time elapsed in that case is simply 2 hours. The distance travel is 150 kilometers. Okay, so that is the how you're supposed to deal with different types of problems. Okay, so now, okay, let's have the formula. Okay, I think V bar, okay, there's a bar on top, so that determines that it is an average. So V bar, okay, this bar here should be on top of this V, okay, and that is equal to delta X over delta T, and that is equal to XF minus XI over T. All right, so final position minus the initial position. So this is the formula for the average velocity. Okay, so let's now have some examples. Okay, so a squirrel runs in a straight line, westerly direction from one tree to another, covering 55 meters in 32 seconds. Calculate the squirrel's average velocity. Okay, so V average, so I cannot place a bar on top, so just say V with the sub AVG. So this is average. Okay, average velocity is equal to delta X over delta T. Okay, so delta X here in this case is covering 55 meters. So from the word itself, covering 55 meters, so this is the distance it traveled, okay, in this 32 seconds. Okay, so 55 meters divided by 32 seconds. All right, so the answer is, okay, it is already rounded off to the first decimal, so 1.7 meters per seconds. And since it's moving towards the left, yes, towards the left or towards the west, okay, so the final answer must be 1.7 meters per second west direction. Okay, so because, okay, we're tasked to calculate the squirrel's average velocity. So if just simply the speed of the squirrel, hence, we can just place our answer equal to 1.7 meter per seconds. Okay, so that is for the velocity. Okay, so right now we'll be dealing with interpreting graphs. Okay, so how can we interpret velocity out of this position versus time graphs? Okay, so other term ani, okay, the other term for this position versus time graph is X versus T. Okay, X versus T graphs. Okay, and it can be written as X dash T graphs. Okay, so let me, okay, by notes. All right, so I think I cannot annotate. Wait, I'm looking for the annotation. Okay, so here we got, okay, annotation. Where are you? Okay. Okay, so I cannot find the annotation. I think I don't know where is it. Annotation. Okay, so let's just continue. Average velocity. We can find average velocity out of this position versus time graphs. Okay. So first, let's determine the average velocity from the initial time 0 until it reaches the final time 15 seconds. So as you can see, the first dot here below located at 0, 0, and this red dot here, that is the final position, okay, at 15 seconds. Okay, so it is in line with the time 15 seconds. So how do we calculate the average velocity? Okay, so let me annotate. Okay, I cannot. All right. So here in this case, let's first have the position. Okay. Initial position just simply 0. So meaning the final position is just our answer. Okay, because final minus initial, since initial is 0, so it's just simply the final. So what is the position at the final? So as you can see here, it is in line with the 6. Okay, so this is 6. All right, so let me check this. Let me check if this is kilometers. All right, so this is in kilometers. That's right. So this graph here is in kilometers and the time is in minutes. Okay, so this 15 minutes, this 15 here is actually 15 minutes. And this position here is in kilometers. Okay, so let's determine, okay, the position at the 15 seconds. So the position is at 6 kilometers and then the time is 15 seconds. So just simply divide 6 divided by 15. That is our answer for the average velocity, okay, of the motion. Okay, so I'll be sharing the whiteboard. Okay, so average velocity, by the way, is equal to delta caps lock, delta x divided by delta t. Okay, so this is the formula. Okay, delta x over delta t. Okay, so if we're going to expand this formula, so actually this should be equal to x sub f minus x sub I, okay, divided by the time. Okay, because initial time is just equal to 0, so just simply t. Okay, so this is the formula we're going to have here, and then equals and then the final position at in that case in the graph is 6 kilometers and the initial is 0. So just simply take out 0 and then place 6 kilometers and we got 15 minutes in the time. Okay, so we can now solve you can just simply divide. So what is the answer for this? 6 divided by 15. So that should be equal to 2 over 5. And 40. Yeah, that's right, 0.40. Okay, wait. Yeah. The answer is equal to 0.40 kilometers per minute. Okay. So this is the answer for the average velocity of that vehicle. Okay. With that is being the motion is being plotted in the graph. Okay. So the answer is equal to 0.40 kilometers per minute. Okay, so let me reshare my slide. Okay, so going back, let's have the next one. Velocity can be interpreted graphically. Okay, so average velocity is actually the slope Okay, it is actually the slope, okay, of the position versus time graph. Again, average velocity is actually the slope of a position versus time graph. Okay, so what is the formula for slope? Anyone? Okay, you can still remember the formula for the slope. Okay, so we have a number line. Okay, let's just say we had a line, straight line, diagonal. Okay, and how do you determine the slope? Okay, of one point to another point. Anyone? Okay, you can still remember the R over R. Okay, what do you mean by that? R over R. You can still remember. Okay. All right. So, okay, I think you already forgotten this. So, slope is actually equal to, let's say, rise over run. Okay. The rise is just say the way it moves up or down. Okay. It depends if it start moving upwards or downwards. And then for the run is simply left or right. Okay. In this case, okay, so we're looking for the average velocity between 3 minutes to 8 minutes. Okay, so the 3 minute here, this is the starting point, and then we're going to rise over run. So to reach the 8 minute mark here, we need to do okay a run to the right and rise upwards. Okay, so meaning all of them are positive. Okay, so you don't need to consider negative answer here. So because to the right and upwards are both positive. All right. So first, let's determine how much it rises. Okay. So in this case, um, this 3 here is actually 1.5, and then it rises around. Okay. Let's just say, okay, this is near 3. So 1.5 towards the 3. Okay, that's the reason why the delta distance okay upwards is 1.5 kilometers. Okay, and then let's check for the delta time. So it started at 3 minutes and then it ends up at 8 minutes. So the delta time in this case is 5 minutes. Okay, and place it in the formula for the slope, rise over run. Okay, 1.5 kilometers divided by 5 minutes. And the answer is equal to 0.3 kilometers per minute. Okay, so that's how you determine the average velocity. Okay, so questions. Any questions? Questions regarding how we're going to interpret the average velocity out of this graph, position versus time graph. Anyone? Questions? Clarifications? Violent reactions? Joke. Okay, so let's have Joshua.
Pwede i-repeat tong sa pag-interpret sa graph, sir.
All right,
Pwede
so let's, yes, that's okay. I can do that. So it is much better if, okay, I'll be take a screenshot of this and let's annotate it using a whiteboard. Okay, so ako sa screenshot. Let me have a quick screenshot of this capture and then let me share this one. Okay, where is that file now? Okay, wait, okay, the file is still opening. Wait. My PC is a bit lagging right now, so okay, please be patient. Okay, can you see? Can you now see my screenshot? Yeah, this the screen right now. Yeah. Okay, so let me annotate this one. Annotate, yes, I can now annotate. Annotate, yes. So first, okay, the formula is always this one. Okay, the formula for slope is slope. Okay, we have the formula for slope, and that is rise over run. Okay, so in a simpler term, it is y over x with the direction. Okay, so just remember, if it's going upwards, positive y, and it is going downwards, negative y, and do the same with the x. Okay, so this is the formula for the slope. Rise over run, or just simply y over x. And then here, we can now determine, okay, this 3. Okay, this is our starting point. Okay, this part is our starting point, and this part here is our end point. Okay, so if we're going to look at the graph, so this point here is actually located in between 1 and 2. So let's have it as 1.5. Okay, and the final point here is, let's just say it is 3 kilometers. Okay, 3.0. So meaning, if you're going to calculate the delta distance, okay, just simply subtract final minus initial. Okay, the final time is 8 minutes, so the position at that 8-minute mark is 3 kilometers. And then subtract it with the initial 3-minute mark, okay, position at that point is 1.5 kilometers. So the answer is equal to 1.5 kilometers. So this is what we call our rise, okay, or the y, okay. And then let's have the x, or the run of the slope. To determine the run of the slope, okay, we need to look at the horizontal component. So the horizontal component is the time, so meaning it started from 3 and ends up at 8 minutes. So to calculate the delta time, so just simply subtract final 8 minutes minus the initial 3 minutes. So the answer is equal to 5 minutes. So this is the run. Okay, so substitute the values here. 1.5 kilometers divided by 5 minutes, and the answer is equal to 0.3 kilometers per minute. Okay, so that is the slope, or in other words, that is the average velocity, okay, in a position versus time graph. Okay, so this is the shortcut, position versus time graph. Okay, if we're going to name a particular graph, okay, it always starts y versus x. Okay, so that is the notation, okay, of plotting the graphs. Okay, the notation is always be, okay, the dependent variable, okay, should be placed first, and then the independent variable, okay, is placed next. Okay, so in this case, always remember, okay, the position changes as time changes. So the independent variable here is of course the time, and the dependent rather is the position. Okay, so any more questions regarding the how to calculate average velocity from a position versus time graphs? Questions? Violent reactions? Okay, volcanic eruptions. Joke. So let's now proceed to next. Okay, let me reshare my slide. Okay. So a while ago, we already calculated the average velocity for the entire trip. Okay. So that's what I had calculated in the absolute board. Okay, a while ago. The distance is 6 kilometers. As you can see, it started at 0. Okay, so meaning the delta distance here just simply 6. Okay, just use the final position, which is 6, and then the final time, okay, is 15 minutes. So for the entire trip, 6 divided 15 is equal to 0.40, or just 0.4 kilometers per hour. Kilometers per minute rather. Okay, so that is the average velocity for the entire trip. Okay, so let's determine your understanding right now. Okay, how much you have learned or how much you have understood regarding the position versus time graphs. So we have here lines. These are the motion of an object in a position versus time graph. Okay, line A, B, C, and D. Which among them first is object at rest? What do you think? Anyone? Okay, you can directly answer if you have the
Lines.
answer.
Letter
Yes,
C.
Leon.
C.
Letter C. Yeah, that's right. Okay, line C. Okay, can you give me the reason why the object is at rest? Anyone? Okay, it's just an instinct that just by looking at letters.
Line, sir.
Straight line. Okay, everything here is a straight line. Okay.
No specific motion, sir.
Okay, no specific motion. Okay, we cannot really determine the motion just by looking at this one. There's a specific reason behind this. Let's have Joshua. What do you think?
Nag-change yung time, sir, pero yung position kay steady. Sir.
Okay, so that is one of the great answers. So the position is steady while the time changes. That's right. However, there's a much bigger, you say, related to my discussion a while ago, reason behind why letter C is object at rest. Okay, anyone who can guess? Okay, who can guess that biggest reason? What do you think is the biggest reason? Okay, so a while ago, we're talking about slope. What is the slope of letter C? Okay, anyone who can answer me? What is the slope of C? Who can answer me? What is the slope? Yes, that's right, 0. Okay, because there's no rise. Okay, there's no rise, meaning there's no y component. So meaning rise over run, 0 over the run. So it is equal to 0. Hence, there is no slope. That is the biggest reason why the object is at rest. All right. So let's now proceed to traveling slowly in a positive direction. What do you think among the next three? Okay, the other three graphs. Anyone? What do you think? A, B, D. What do you think? Slowly. Okay, slowly. Positive direction. So that is the clue. Okay, what do you think is the answer? Anyone? Can just try.
Letter D.
D.
Sir. Yes, Daichi. I can hear you. I can
Letter
clearly.
D.
Letter D. Okay, that's right. The answer is letter D. Okay. Why do you think, Daichi? Okay, can you give me the explanation? Okay, why do you think it is traveling slowly at the positive direction?
Okay, so D and B are the graph which is traveling to positive direction.
That's right. Okay.
And
And
Q.
why do you think that D is slower compared to B?
Since the D is more, the slope is more gentle.
Okay. So compared to B, okay, it is much, okay, the slope is much smaller, okay, compared to B. Okay. So as you can see, okay, the position, okay, the position determines the rise. So meaning rise over the run, it doesn't matter if the run is long because it is in the denominator. So meaning the quickness, okay, the speed depends on how 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 far is the position in the graph. Okay, so that determines also how fast an object is traveling. Okay, so since D is in a shorter, okay, in the shorter position, in the lower position, then okay, it is having a lower slope compared to B. Hence, okay, the answer is letter D in this case. How about the third one, traveling in a negative direction? Traveling in a negative direction.
A, sir.
That's right, letter A. That is the only line that is opposite in direction with the other two. Okay, so just remember, okay, it is going downwards. So meaning the rise here is negative. Okay, and the run, even though the run is going to the right, so it doesn't matter because one of them is already negative. So the slope here is negative, then it is actually traveling in a negative direction. Okay, so how about the last one? So of course, and obviously, the answer is letter B, traveling quickly in a positive direction. As I said a while ago, since the position is okay higher, and then the time hence the slope should have a bigger slope compared to D. Okay, hence B is okay traveling quickly in positive direction. Okay, so right now, okay, this is the moment, okay, that we are waiting for. Joke. So this is the moment by which you need to know, okay, the difference between average and instantaneous velocity. Average is just simply you're going to calculate, okay, the displacement and divide it by the time. That is the average velocity. However, for instantaneous velocity, it is the velocity at any given moment in time or a specific point in the object's path. So, for example, an object is traveling 150 kilometers in 2 hours. What is the instantaneous velocity when the object is at 120 kilometers? We cannot determine that one, okay, unless we know calculus. Okay, so again, we cannot determine, okay, instantaneous velocity without knowing calculus. So in a simpler sense, okay, instantaneous velocity is actually equal to, okay, the limit of the average velocity as time approaches zero. Okay, so let me have some formula. Okay, so okay, share let me share the whiteboard. Okay, so for instantaneous velocity, instant Okay, can you still remember limits and derivatives, calculus? Okay, anyone, can you still remember them? All right, so instantaneous velocity is actually the limit of the average velocity as the time interval approaches zero. Okay, so let's just say time interval. Okay, approaches 0. So this is the instantaneous velocity. Why is it the limit of the average velocity? Because, okay, instantaneous meaning we want to know what is the speed at that particular instant of time. All right, so we need to make sure that there is no difference of time, there is no time interval. So that's the reason why we need to calculate the limit of this average velocity such that the time interval right now is approaching 0. Okay, so we can also create another formula for this. Let me copy this one. Okay, copy, and then we can have a formula. Okay, so we can change delta average as this one. Okay, remember this is the formula for the average velocity. Okay, loading. Wait, Pandora. Okay, so in a sense, is actually this is the limit. Okay, delta x over delta t. Okay, as delta t approaches 0. Right now, we cannot calculate really delta t. If we're going to simply substitute delta t here with 0, okay, we're going to have an answer equal to infinity. However, okay, we can still calculate it if we're going to translate limits into derivatives. Okay, so limits into derivatives, so it is actually equal to the derivative of the position with respect to time. Again, it is the derivative of the position relative to the time. Okay, so if there's a given position equation, we need to take its derivative with respect to time. Hence, we can now determine the instantaneous velocity just by creating a velocity equation out of the position equation. So, for example, okay, I have here an equation, a position equation. Just let's just say this is the position equation of a car that is traveling in a straight line. Okay, 2t squared, okay, minus 12t plus 9. Okay, so this is the equation of the position equation. So the car is traveling, okay, according to this equation. So we have an equation here. And then how do we calculate, okay, how do we calculate the average velocity? The instantaneous velocity. Okay, so let's just say, remember, average velocity is being denoted as V bar, okay, V with a bar on top, or V average, V sub average, okay. For instantaneous velocity, we can just simply write it as V, okay. We can simply write it as V, okay. So this is the symbol for average velocity, okay. Since velocity is also a function of time, so I just place here velocity V of t, okay. And then remember the formula is dx over dt, okay, derivative of x with respect to t. Okay, so do you still remember the shortcut, okay, how the rule for the derivatives of an exponent of a constant number? Just simply this t, only the variable itself. Okay, can you still remember the rule? Anyone? Okay, do we need a refreshment regarding this part? Okay, the calculus. Okay, you can still remember. Okay, wala may nisa. So I think let's have some refreshments. Okay, so let me have a new page. So for example, I have here x is equal to the function of x squared plus 5x plus 10. Okay, so can you still remember f prime of x? Okay, this is all another way of writing the derivative. Okay, so f prime of x is the derivative of f of x. So here we're going to apply different rules. First is the exponent rule. We can also apply exponent rule here in the second term. So, but still there's a simpler way of solving when the variable itself is the given. Okay, so let's first have the exponent rule of the derivatives. Okay, so exponent rule of derivatives. Okay, so in an exponent rule, okay, if I have here an exponent, so I'll just place, okay, something like this. Okay, this is, okay. So this is the derivative of this equation with respect to x. Okay, remember the variable here is x. So we need to derive it with respect to the variable itself. If the variable is not the same, hence the answer is equal to 0 because we will consider this as a constant. Okay, because it is not a function of that particular variable. All right, so now we're going to have, okay, the rule. Okay, the rule is that you're going to take the exponent, multiply it with the coefficient of the variable x cubed. Okay, so take the exponent and multiply it with a coefficient. And then the next step here is copy the variable. However, the exponent now will be subtracted by 1. All right, so this should be to the power of 3 minus 1. Okay, so this is the rule, okay, for the exponent. Okay, so let's continue. So let's simplify this one. This should be 9x to the power of 2. 9x squared. Okay, so this is the derivative rule. And what if, okay, I have here simply 7x. Okay, there's no exponent at all. Okay, so we're going to follow the rule itself. Okay, the exponent of x is simply 1. Okay, so 1, multiply it with the coefficient 7, and then copy the x, and then the exponent is 1 minus 1. Okay, we're just following the rule for the exponent. Okay, so we got here 1 times 7 is 7, and then 1 minus 1 is 0. When any variable or number being raised to 0, the answer is always equal to 1. Okay, so you simply times 1, and the answer is 7. Okay, so meaning the simpler step, okay, if the given is only the variable itself, just take out that variable and just copy the coefficient. That is the shortcut, okay, in getting the derivative, okay, of a variable of a quantity or a term with a variable, okay, with the power of 1. And for the constant, just remember, for a constant, the answer is always 0. Okay, so the derivative of a constant is always equal to 0. Okay. Derivative of a constant is always equal to 0. So now we can now answer what is the derivative of this equation. Okay, anyone who can give me the answer? Yes, Leah.
Right, sir. 2x plus 5.
Okay, that's correct. 2x plus 5. Okay, excellent. You got it right. Okay, so how about this? Okay, let me check your understanding. So let me up it up with few variables. Okay, taas na kayo shut up. Okay, so all right, how about this one? Can you still do a mental calculation here? Yes, you can. Okay. So what do you think is the answer? Yes, Leah.
Answer.
Hmm.
12x cubed minus 21x squared minus 4x.
Okay, that's correct. Okay, so you can do a mental calculation. So just first multiply 4. Okay, just do multiplying 4 with 3. Then hence you get 12 and take 1 from 4. You get 3 exponent. And then just copy the signs. Negative 7 and then 3, 21. Take 1 from 3. You get 2. And then here 2 times 2 is 4. Take 1 here, just simply x. And then a constant is 0. Okay, just take it out. So that is how you're going to do derivatives in yes, derivatives using the exponent. Okay, and by the way, I just going to limit calculus at this point, so I will not be tackling over harder chain rule. Okay, if you still remember the chain rules. Okay, so we're not tackling them here in the problem. So we only want to know how to determine instantaneous velocity out of this. Okay, so here are the formula. Okay, so going back, so let's calculate. Okay, what should be the answer here? Okay, the only difference right now is we're deriving it. We're doing a derivative with respect to time. So of course, going to derive it with respect to the variable t. So what do you think is the answer here? So we're going to replace x into the equation inside. Okay, I'm just going to copy this. Wait. Just going to copy everything and derive it with respect to time. So what do you think is the answer? We can do a mental calculation. Okay, so 2 times 2 is 4. Okay, take 1 from the exponent 2. Okay, just simply 1. And then just take the variable, take the coefficient of this, take out the variable. Okay, 12. And then for the constant is simply 0. Okay, so this is the answer for the velocity equation. Okay, so this is now our velocity equation. Okay, so we can now derive velocity equation out from the position equation. Okay, position equation. All right, any questions regarding this instantaneous velocity? Okay, and before we end, let's have an example for the instantaneous velocity. Okay, a simple example. Okay, so we're just going to make use of our answers here. Okay, so I'll just going to copy this one. Okay, for example, my problem is a car is traveling according to the equation, this equation. Okay, and then let's find the instantaneous velocity. Okay, 5 seconds. Okay, and then let's have a bit harder problem. Find the position object when the car stops moving. All right. So let's solve this two problem. Okay, one easier and the other is a bit, okay, it requires critical thinking. So first, let's have this one. Let's find out the instantaneous velocity, okay, at t is equal to 5 seconds. So we know the position equation, okay? We know this one. This is already given. And then, since we're looking for the instantaneous velocity, so we need to solve for instantaneous velocity. Okay, I'll just placing x prime of t. Okay, so this x prime of t is just simply dx over dt. Okay, so that is other way of rewriting derivatives. So the derivative of the equation x of t is, we already solved it a while ago, 4t minus 12. Okay, so this is our velocity equation. Okay, and right now, we just simply substitute, okay, to solve for a, we just simply substitute t is equal to 5 seconds. Okay, I forgot to place where x is in meters. Okay, so that we know the velocity. Then the velocity is meter and the position is in meters and the time is in seconds. So now, how do we calculate the instantaneous velocity? So using the velocity equation, v of t is equal to 4t minus 12, then we're going to find out what is v of 5. Okay, so to solve for v of 5, just substitute t with 5 and manipulate the data. So 20 minus 12 is 8. And then place the unit, 8 meter per second. So this is now our answer, okay, for this letter A. This is our answer. Then also for letter B. Letter B. Okay, how do we determine letter B? So what are the given for letter B? Position, we're looking for the position of the object. Okay, and then car stops moving. So what can you determine from this line? Car stops moving. Okay, so what variable can we determine here? Anyone who can tell me what is not moving here? What particular physical quantity is not moving here? Anyone?
It means velocity is 0.
That's right. It means that the velocity is 0. Okay, great. Daichi, so v is equal to 0. Hence, we're going to determine the time for the velocity equal to 0. Then we're going to substitute it to the position equation. Okay, and we're going to find out the position at which the velocity is 0. So the formula is v of t is equal to 4t minus 12. And then since v is 0, so just place 0 there and then equals 4t minus 12. Okay, so I'll be transposing negative 12 to the other side and switch the sides. So meaning there's no change in sign if you're going to switch sides. So we can do this, 4t is equal to 12. And we got t is equal to 3 seconds. Okay, so we're going to follow the convention. We have 3.0 seconds. Okay, so we're going to follow the convention in the given, okay, later on. So now, let's do, since we're still not done here yet because we need to know the position of the object when a car stops moving. Hence, it only stops moving when t is equal to 3 seconds. So let's find out, okay, the position at 3 seconds. Okay, so we know this is the position equation. So x of 3, substitute 3 squared to the power of 2 minus 12 times 2. 12 times 3. plus 9. Am I right? So t replaced with 3, 3, yes, 3. Okay, so what is now x of 3 here in this case? Okay, so this is 9, so 18 minus 36 plus 9. Okay, so 27 minus 36 is negative 9. Okay, am I right? Yeah. So negative 9 meters. So this is the position of an object, okay, when the car stops moving. Okay, so that is our answer. Okay, so the negative sign determines that the object is simply at the left side of the graph. Okay, so the negative sign here determines that the object is at the negative side of the graph, at the negative 9 position. All right, so any more questions regarding this problem, sample problem for the instantaneous velocity? Questions? Okay, are you sure? Oh, yes, question.
Kanang sabi, ay kaning sa time equals 3.0 seconds, sir ba? 2 sigfig dyan na siya or okay rag 3 seconds?
Yes, okay, around 3 seconds. Okay, wala pa mo kuningon. Okay, I'm still not giving you some proper significant digits to follow. Okay, just place it as simply 3 or 3.0. Okay, I'm just following what is the given 5.0 here, so I can place 3.0. Okay, in this case, however, 3 is still okay. 3 is still correct. Okay, so any more clarifications, questions? Okay, hesitations? Okay, so wala na. Okay, I think there's no more questions. Okay, so right now, this is all for today. Let's continue, okay, with the next topics. Okay, the next topic is regarding average and instantaneous acceleration. And we'll be doing some word problems tomorrow, okay, after we are done discussing average and instantaneous acceleration. And by next week, okay, the next week, okay, we'll be having a bit longer topic, okay, motion, okay, with constant acceleration and a free fall motion. Okay, so hopefully you still be here again. Okay, so it is much better if you join my Zoom meeting, because okay, any doubts or any questions you might encounter during the meeting can be answered right away, okay, by me. Okay, so I think this is all for today. Okay, thank you for coming, everyone. Class is dismissed. Goodbye, everyone. Thank you for
Bye,
coming.
sir.
Bye, sir.
Bye, sir.
Thank you.
Sir.
Okay, you can now leave the Zoom meeting. Thank you.